So let's think a little bit about the Maxwell-Boltzmann distribution. And this right over here, this is a picture of James Clerk Maxwell, and I really like this picture. It's with his wife, Catherine Maxwell, and I guess this is their dog. And James Maxwell, he is a titan of physics, famous for Maxwell's equations. He also did some of the foundational work on color photography, and he was involved in thinking about, well, what's the distribution of speeds of air particles, of idealized gas particles. And this gentleman over here, this is Ludwig Boltzmann, and he's considered the father, or one of the founding fathers of statistical mechanics. And together, through the Maxwell-Boltzmann distribution, they didn't collaborate, but they independently came to the same distribution. They were able to describe, well, what's the distribution of the speeds of air particles? So let's back up a little bit, or let's just do a little bit of a thought experiment. So let's say that I have a container here. Let's say that I have a container here, and let's say it has air. And air is actually made up mostly of nitrogen. Let's just say it just has only nitrogen in it, just to simplify things. So let me just draw some nitrogen molecules in there. And let's say that I have a thermometer. I put a thermometer in there, and the thermometer, it reads a temperature of 300 Kelvin. What does this temperature of 300 Kelvin mean? Well, in our everyday life, we have a kind of a visceral sense of temperature. Hey, I don't want to touch something that's hot. It's going to burn me. Or that cold thing, it's going to make me shiver. And that's how our brain processes this thing called temperature. But what's actually going on at a molecular scale? Well, temperature, one way to think about temperature, and this would be a very accurate way to think about temperature, is that I'm spelling it wrong, temperature is proportional to average kinetic energy of the molecules in that system. So let me write it this way. Temperature is proportional to average kinetic energy. Average kinetic energy in the system. I'll just write average kinetic energy. So let's make that a little bit more concrete. So let's say that I have two containers. So it's one container, and two containers right over here. And let's say they have the same number of molecules of nitrogen gas, and I'm just going to draw 10 here. This obviously is not realistic. You'd have many, many more molecules. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And let's say we know that the temperature here is 300 Kelvin, and the temperature of this system is 300 Kelvin, and the temperature of this system is 200 Kelvin. So if I wanted to visualize what these molecules are doing, they're all moving around, they're bumping, they don't all move together in unison. The average kinetic energy of the molecules in this system is going to be higher. And so maybe you have this molecule is moving in that direction. So that's its velocity. This one has this velocity. This one's going there. This one might not be moving much at all. This one might be going really fast that way. This one might be going super fast that way. This is doing that. This is doing that. This is doing that. So if you were to now compare it to this system you could still have a molecule that is going really fast. Maybe this molecule is going faster than any of the molecules over here, but on average the molecules here have a lower kinetic energy. So this one maybe is doing this. I'm going to see if I can draw on average. They're going to have a lower kinetic energy. That doesn't mean all of these molecules are necessarily slower than all of these molecules or have lower kinetic energy than all of these molecules, but on average, they are going to have less kinetic energy. And we can actually draw a distribution. And this distribution, that is the Maxwell-Boltzmann distribution. So if let me draw a little coordinate plane here. So let me draw a coordinate plane. So if on this axis I were to put speed, and on this axis I would put number of molecules. Number of molecules right over here. For this system, the system that is at 300 Kelvin, the distribution might look like this. So it might look, the distribution, let me do this in a new color. So the distribution, this is going to be all of the molecules. The distribution might look like this. might look like this. And this would actually be the Maxwell-Boltzmann distribution for this system. For system, let's call this system A. System A right over here. And this system that has a lower temperature, which means it also has a lower kinetic energy, the distribution of its particles, so the most likely, the most probable, you're going to have the highest number of molecules at a slower speed. Let's say you're going to have it at this speed right over here. So its distribution might look something like this. Now, so it might look something like that. Now, why is this one? It might make sense to you that, okay, the most probable, the speed at which I have the most molecules, I get that that's going to be lower than the speed at which I have the most molecules in system A, because well, these, on average, these things have less kinetic energy. They're going to have less speed. But why is this peak higher? Well, you got to remember, we're talking about the same number of molecules. So if you have the same number of molecules, that means that the areas under these curves need to be the same. So if this one is narrower, it's going to be taller. And if I were to somehow raise the temperature of this system even more, let's say I create a third system, or I get this, or let's say I were to heat it up to 400 Kelvin, well then my distribution would look something like this. So this is if I heated it up. Heated up. And so this is all the Maxwell-Boltzmann distribution is. I'm not giving you the more involved, hairy equation for it, but really the idea of what it is. And it's a pretty neat idea. And actually, when you actually think about the actual speeds of some of these particles, even in the air around you, you might say, oh, it looks pretty stationary to me. But it turns out, and the air around you is mostly nitrogen, that the most probable speed of, if you picked a random nitrogen molecule around you right now, so the most probable speed, and I'm going to write this down because this is pretty mind-blowing. Most probable speed at room temperature, probable speed of N2 at room temperature. So let's say that this was the Maxwell-Boltzmann distribution for nitrogen at room temperature. Let's say we call room temperature 300 Kelvin. This most probable speed right over here, the one where we have the most molecules, the one where we're going to have the most molecules at that speed. In fact, guess what that is going to be before I tell you, because it's actually mind-boggling. Well, it turns out that it is approximately 400 and actually at 300 Kelvin, it's going to be 422 meters per second. 422 meters per second. Imagine something traveling 422 meters in a second. And if you're used to thinking in terms of miles per hour, this is approximately 944 miles per hour. So right now, around you, you have actually, the most probable, the highest number of the nitrogen molecules around you are traveling at roughly this speed, and they're bumping into you. That's actually what's giving you air pressure. And not just that speed, there are actually ones that are traveling even faster than that, even faster than 422 meters per second, even faster. There's particles around you traveling faster than 1,000 miles per hour, and they are bumping into your body as we speak. And you might say, well, why doesn't that hurt? Well, that gives you a sense of how small the mass of a nitrogen molecule is, that it can bump into you at 1,000 miles per hour, and you really don't feel it. It feels just like the ambient air pressure. Now, when you first look at this, you're like, wait, 422 meters per second, that's faster than the speed of sound. The speed of sound is around 340 meters per second. Well, how can this be? Well, just think about it. Sound is transmitted through the air through collisions of particles. So the particles themselves have to be moving, or at least some of them, have to be moving faster than the speed of sound. So not all of the things around you are moving this fast, and they're moving in all different directions. Some of them might not be moving much at all, but some are moving quite incredibly fast. So I don't know, I find that a little bit mind-blowing.